let me introduce Dr. Shuxue Quan. And Dr. Shuxue Quan is the Senior Director of Research in Computer Vision and Augmented Reality at OPPO US Research Center, where he built and leads the team of developing algorithm of slime, scene understanding, 3D reconstruction, human-computer interaction, and computational photography. And his team also built software frameworks and applications to enable AR on mobile devices and head-mounted devices. Before OPPO, he was a principal engineer at Qualcomm and on computer vision and machine learning and mobile cameras, and after a few positions in Sony, Macron, and Broadcom. Dr. Quan received his MS and BS on optical engineering from Beijing Institute of Technology and a PhD in imaging science from Rochester Institute of Technology, as my background image shows. Dr. Quan has granted more than 60 patents and academic papers. From the most recent market review, OPPO is the 4th largest mobile phone company in the world. And remarkably, his team takes the major computer vision research within the company. So he will give us an introduction from the industry research perspective based on his team's research outcome, which may appear in the future OPPO mobile phones very soon. Okay, welcome, Dr. Quan.
Thank you, Dr. Lu, for the introduction. Good afternoon, everyone. Thank the SLAM workshop community giving me this opportunity to give a talk on building the SLAM system for smartphone and AR glass. So the content of this talk is very different from the previous ones. I focus more on the implementation side on mobile platforms to commercialize SLAM algorithms. So first, I give a brief introduction to my current employer, OPPO. So OPPO is one of the major smartphone makers in the world. It ranked #2 in China and #5 in the world in terms of shipment last year. So if you don't know OPPO, you may know more OnePlus. So OPPO is a parent company of OnePlus. So augmented reality, to my knowledge, first described in this paper by Boeing engineers in 1992. So which is elaborated the 3 features of AR. First, the 6 degrees of freedom tracking for head-mounted display, and the second, the real-time and photorealistic fusion of virtual of graphical information and real scene. Third, the interaction with the control software may occur through voice input. Actually, I mean, current days also the hand gesture is also a major input interaction approach. Since then, AR has been an active academic research topic. It also has certain applications in industry these days, and also education and the medical area. So AR becomes well-known and popular when Pokemon Go was released in 2016. The interest of AR for consumers was ignited since then. Today, AR picture and the video has been everyday habit for many selfie likers. The history of smartphone AR is listed below. In 2017, because they released announcement of AR Kit and ARCore, it was typically called the beginning of smartphone AR. However, actually in the earlier times, like in 2010, 2012, Qualcomm has the so-called Euphoria SDK. It was still there, becomes a part of the PTC company. And in 2014, Google released the Tango. It's also for mobile device. And then later, like since AR engine, OPPO AR unit, Snapchat, and so on, and also the so-called real-world AR platform was announced, and it becomes like a very active for consumers. And So in 2017, when the ARCore was announced, the AR on smartphone slowly becomes popular. So in the table below, the major components of Apple's ARCore are listed and categorized. The essential components of ARCore are VLO or visual SLAM, surface detection, and light estimation. There are some additional APIs like image detection, tracking, object reconstruction, face tracking, and also for output display and the user experience. So the ARCore on Android, in the table below, the major components of Google's ARCore are also listed and categorized. So the essential components of ARCore are motion tracking, environment understanding, and light estimation. So the motion tracking allows the phone to understand and track its position relative to the world. So it's essentially the VLO6 stuff. Environmental understanding allows the phone to detect the size and location of all typical surfaces, horizontal, vertical, and angled surfaces like the ground and so on. Light estimation allows the phone to estimate the environment's current lighting conditions. There are other AR SDKs like the Euphoria I just mentioned, which was part of Qualcomm's AR strategy. Euphoria, and currently it has a cross-platform support on iOS, Android, and Windows. So again, the essential component in Euphoria is a SLAM or VLO. The technologies for augmented reality are placed here as icons. You can see like a SLAM, visual inertial navigation, camera calibration, camera eccentrics. Those are for the sensor calibration and the sensor fusion, and then surface estimation, and the nonlinear optimization and bound adjustment are for the post-processing of the visual SLAM. The major SLAM algorithms, other than deep learning based, are put here along the time axis. We have been paying more attention to the OPPO SLAM and WINS Mono due to their published performance and technology details and the availability of the open source code. So here you can see the SLAM as a new concept that was proposed in 1986, and in recent years, like WINS Mono in 2017 and the DSO direct sparse odometry in 2018, and then in recent years, deep learning based SLAM algorithms are popped out. So this SLAM algorithm was published. It's called WINS Mono in 2017. The whole process starts with measurement pre-processing with camera at 25 Hertz and IMU at 100 Hertz. This frequency can be higher for some devices. And for camera, there's a feature detection and tracking, and IMU, there's a pre-integration. And then the data was sent for initialization, and then to the local visual inertial odometry with the relocalization, and later the second the backend is global post graph optimization and the map reuse, and after that the output is sent to the motion bound adjustment, and for propagation the output is a camera rate post estimation and IMU rate post estimation. So why need to build our own SLAM algorithm, a SLAM system? As I mentioned, Google's ARCore is available on many Android devices. So first, we can see like one SLAM system can be applicable to multiple areas. So on the diagram about the SLAM algorithm, actually can be applied to XR head-mounted devices, can be applied to also drone, sweeping robotics, and the smartphone. The major difference is the sensors. Like for smartphone, it's a single camera plus IMU. For XR head-mounted display, it's multiple fisheye cameras plus IMU. And the drone is the dual cameras plus IMU. And the sweeping robotics is mono fisheye plus a step motor. So this is Google ARCore and the Qualcomm XR solutions. So on smartphone, Google ARCore supports smartphone, but it does not support AR Glass. And then Qualcomm's XR, it supports AR Glass, but does not smartphone. So at OPPO, we want to build like a unified SLAM system for both the smartphone and the AR Glass. So on the right side is the illustration of the key smartphone AR components where SIM or VIO is in the center. So to build a SLAM for smartphone, we need to set up lab to calibrate the sensors and also evaluate algorithm iterations and benchmark it against competitive solutions. So these are actually compared with academic research, we need to have this kind of online performance. Online performance, then the algorithm is tightly coupled with the sensor intrinsic parameters, that is camera and IMU, and also the evaluation of the algorithms. We need to do it with the grounded truth data, and also we have a method to do side-by-side comparison. Also, since we want to run the algorithms on mobile devices like a smartphone or AR Glass, so the algorithm optimization and acceleration is very important. So this involves the removal of third-party like a software dependency, like a Boost, OpenCV, and so on. And also we need to take advantage of the hardware acceleration, specifically on smartphone and AR Glass, like the ARM and near acceleration, DSP, and HVX acceleration. HVX is Qualcomm's Snapdragon hexagon vector accelerator, and then OpenCL, OpenGL, and so on. So the input of the to the SLAM is camera images, IMU, and also could be GPS, time of flight, depth sensor, and the stereo cameras. So here, one of the major difference to evaluate the SLAM algorithms is to, yeah. So this is the initialization for the algorithm to start work. So we, like I just mentioned, we evaluate on real devices instead of evaluate with offline data set. So here we have actually 3 solutions. The left is running ARCore on a device on the same device, and the middle is like a previous SLAM solution developed at OPPO, and the right is our current solution. So you can see our current solution is very close to ARCore visually, and somehow the middle solution, that is our previous generation, messed up. So to measure the performance more accurately and repeatable, we use a robot to follow certain predefined paths, and the ground truth data were collected with a Vicon system. So you can see the difference between manual data collection versus data collection by robot. The data collection by robot, it's we can have repeatable data, and also the motion control, the control in rotation speed, translation speed, and the motion pattern can be programmed. And also the environment is not limited to Vicon. It can be like an outdoor. So this, I think it was just played. So the Vicon system was installed, mounted on the ceilings and surrounding the center, the empty space. So here actually we compare the OPPO Iris SLAM system with the ARCore. Here we have like a square path with normal speed, like a normal working speed. The ARCore performance and the Iris camera performance are compared side by side on the right two columns, the position arrow and the rotation arrow. The position arrow actually is about the translation, and the rotation arrow is about the accuracy of a rotation. So in this square path, for our solution, the translation is arrow is larger than the ARCore, and the rotation arrow is slightly smaller than the ARCore solution. Then with a different path, the circle path still normal motion. Normal motion, we found here the translation on the second to the last column. The translation arrow is also larger than ARCore. The rotation arrow is also larger, slightly larger, maybe 15%. So this is like another different path. We want to test it out on different paths because it involves different kind of motion and also the rotation. So here, somehow we have better translation accuracy and also rotation accuracy. Somehow the rotation accuracy is much smaller than the ARCore solution. So above we have some observation, like the regular thing, Iris is roughly equivalent to ARCore, and ARCore is more robust than Iris for indoor, and Iris is slightly more robust than ARCore for outdoor. So this is another path. It's like a 8 shape. So let's see for ARCore and Iris, the translation arrow is roughly the same. However, in this shape, somehow our Iris solution, the rotation accuracy is worse than ARCore. It's 1.55 versus 3.43. So this is another path. It's like a long path with back and forth. Then it involves dramatic rotation on the two ends. So here for ARCore and Iris, the rotation for Iris is better than ARCore, but the rotation is about like 50% worse in terms of the rotation, the angle, the degree of rotation. So this is like a stress test. We still have like this square shape, but then we have like a fast motion, and we turn around and also fast motion. The Iris performance for the translation is kind of much worse than ARCore, and also the rotation angle is not as good as ARCore. And also the slow motion is another stress test for slow long distance square motion. The translation error is about the same. No, the translation error is about the same, but the rotation accuracy is worse than ARCore. So the algorithm is continuously evolving and improving, and also we try to make it work on like AR glass. So at the end of last year, OPPO becomes the very first major smartphone vendor to announce like AR glass. So on the right side is the sensor components of the AR glass. We have two symmetrical fisheye cameras, and also in the middle there's a top depth camera and also a main RGB camera. So the algorithm, instead of running through the RGB camera plus IMU, we need to run the algorithm to run it with the dual fisheye cameras and also plus IMU. The sensor calibration becomes more complex because it's a fisheye camera and it has two cameras, and also we need to make like a time stamping for the two fisheye cameras and also the IMU motion sensor. And the latency of SLAM is critical. The long electron to photon latency will cause dizziness for many wearers. If that's a typical problem for AR's adoption by people. And then because it's like a wearable device, the power consumption is also a top priority. The algorithm optimization and acceleration with available hardware components is very important. And here, actually, we have some solution on Qualcomm's Snapdragon chipset. The SLAM algorithm acceleration can be achieved through two ways. One is use the FastSW library on Neon and the DSP and the HVX. And the second is use the dedicated computer vision processor which is coupled with the DSP and the HVX. Currently, you can see the CVP components, pre-processing and detection. It is support like a pyramid scaler and a feature descriptor, and then the tracking and the motion processing, optical flow, a feature pointer extraction, and a binary feature descriptor, and the inline descriptor matching, and the NCC, and the classification, nonlinear classifier, low power, high quality image warping, and the depth from stereo, scheduling, and the concurrency handling. So on the right side, actually, is like a typical filter-based 6-off algorithm. The feature detector and tractor, this is the major tasks offloaded to the CVP, and then the extended Carlone filter, which will still be done in computer DSP and optionally in modem DSP, because this part it has to use the floating point computation, and it's so in this slide you can see when the CVP and the DSP are used together to offload all the computations from CPU, and this is the partition of the tasks. Like the pyramid scaler with a 3-level pyramid scaler on the CVP, and the feature tracking, basically fast 10 or Hertz corner, and then 3 levels of NCC, and then key point detection, and so on. So these are done on the CVP. The other part is done on the DSP. And from utilizing the CVP, you can see the power savings can be done from purely using only the neon and the DSP from 2x power saving to 4x power savings. So it's a lot to reduce the power consumption and on the head-mounted devices, AR devices. So this is when we modify our algorithms to run on OPPO's AR Glass, and this is the real testing. The engineer is wearing the glass, and the algorithm is running on the glass. And you can see when the engineer turns at the corner of the square, the shape it changed automatically to follow the path. And here is we put like a virtual OPPO logo on the glass, and then we can observe this logo is in a fixed location of the world when we moving around the glass. And on the right side, we have created like a solo system to demonstrate this 6-DoF's performance. So you can see the virtual solo system is very stable on the AR glass. So conclusions and future work. So at OPPO, we have built a unified SLAM system to support both the smartphone and AR glass. The accuracy of the system on the device approximated state of the art, but still on some scenarios it lags behind. We found that the latency and the power consumption is critical for head-mounted devices, and utilize every means of the hardware to accelerate the algorithm and reduce the power consumption. And in the future, to create a more accurate and robust SLAM system, like an AI-based solution may be a better option. With 5G network, the computation can be offloaded to edge computing servers. With this, I concluded my talk. Thank you for your time.
Okay. Thank you, Dr. Quan, for your impressive talk. We have some questions from the audience. One question is how to deploy such a VIO SLAM system when you have low visibility. For example, there is fog or smoke, or there is a low lighting situation.
Yeah, actually, that is a problem. Currently, I think especially for AR glass, it's for indoor application. We currently assume the lighting is in a reasonable condition. The extreme condition currently it doesn't work, and probably need a lot more research and explore the more computation intensive algorithms.
And a follow-up question is, do you think the SLAM sensor will coverage a set of sensors that will be widely used? So by another saying, what kind of sensor is the most important for the SLAM system in your applications?
Currently, I think both the camera sensor and the IMU are they are equally important, because when the features are not useful for camera sensor. We rely on the IMU to make a SLAM work, and then IMU is not as accurate as a camera sensor when the feature points are reached. So both are important. And in addition, I think we also think like a time flat depth sensor can be also very useful. It can reduce the like the initialization time and also the improve the accuracy. So these sensors probably there are more and more sensors to be added to the smartphone and the AR glass. For example, like the event-based sensor, it theoretically and potentially could be very useful. So we expect more sensors to make the system more robust.
Okay. Another question is for AR glasses and the mobile phone, and would be the SLAM algorithm used for those two different platforms be different based on their sensors or based on their computational power difference? Or what is the difference? What could be there some difference between the AR glass platform and the mobile phone platform in the SLAM system?
We found like the dual fish eye for AR glass. Actually, it can see more features, and it can reduce the initialization time, and it also is more robust because the fish eye can see, like I just mentioned, more features, like a much more larger field of view. So other than that, the later part of the algorithms are actually the same.
Okay, and for mobile phone and the AR glasses, what is the most important, the first priority? For example, timing performance and accuracy and memory consumption and power consumption. Which is the first priority you think when you realize a SLAM algorithm on those platforms, and you will consider, for example, compare the timing performance and accuracy and memory and energy. Those several different perspectives.
Yeah, currently I think the application for smartphone and the AR glass, they focus differently. Like for smartphone, the gaming could be like a major application, and also like Animoji. Those things are major applications. So they like surface detection, which is like a post-processing of SLAM, is important. However, on AR glass, the gaming currently is not the major application, and the latency, like I mentioned, the latency from electron to photon is critical, because many people has this motion sickness when wearing the AR glass if the response is slow. So I would say on AR glass, the timing is higher priority, and then the power consumption is the second high priority, because when it generates a lot of heat, it creates some hazard for the wearers.
Okay. Maybe we have time for the last question. That would be for AR glasses and for mobile phones. And which part? How much is the machine itself to compute? For example, and how much SLAM algorithm, which part of the SLAM algorithm is running on the mobile phones, and I believe quite a lot of SLAM algorithm will run in mobile phone. That would be something like on the mobile phone itself. But for AR glasses, many of the computation task is conducted on the server. And but do you have a number or idea, and how much percentage of the computation task is conducted on the machine itself, and how much is conducted on the server?
Currently, I think for the demos and the applications we work on, most of them are conducted locally. The servers have not been used because the slow connection to the server, like a cloud, will cause the algorithm to not run correctly. We need to run the algorithms in real time for both the phone and the AR glass. So in the future, that's what I mentioned. If with a working 5G network, the computation can be offloaded to the servers. But currently, we still expect major computations are done locally, and that's why like a SLAM and even like the hand gesture, they are used for supporting AR applications. So the AR application, we expected to take more resource on GPU and also CPU. So that's why we try to offload the SLAM to run on DSP or even the hardware like a CVP.
Yes, that makes sense. That totally makes sense. But I think in the future, there might be some changes, as you mentioned, with the 5G network, and there could be some difference. A quick question is, will those SLAM algorithms you demoed will be soon on the new generation of OPPO phones?
I hope so, yes.
Okay, great. Thank you very much again, Dr. Chen. And it's an impressive talk. And there will be more questions on the YouTube channel, and you can interact with them. Okay, thank you again.
Yeah, thank you, Dr. Lu. Thank you, everyone.